All right, we are into the second video of Unit 2. We're going to talk about mass today. We're going to look at how to draw free body diagrams, and hopefully we'll get into Newton's three laws of motion. We do have a little cleanup to do at the beginning on types of forces. We had two types of forces we didn't get to include in the last video. So yeah, we'll just keep an eye on the time and see how long things go and hopefully get through all of this. All right, so let's get right into the two types of forces we had not yet listed. So we got gravity, we got normal force already, we got applied, we got tension, and we got friction. So there's two more that we're going to spend some time with. Now, one of them, for these remaining two types of forces, one of them we really aren't going to spend a whole bunch of time with because we've mentioned it a lot, but despite mentioning it quite a bit, we have not worked with it, and that is air resistance. We are going to talk about it because we've mentioned that it could cause acceleration, that in the air things could slow down due to air resistance or drag, but we've danced around it and avoided including it in any of our equations and really don't deal with it for the most part. But we're going to go ahead and do it. So drag force, we'll find this is not limited to just air resistance, but drag in general is a resistive force, or the resistive force so like friction, it resists things. In this case, it resists the motion of the object. So it's a resistive force opposing the motion of an object. And that way it behaves a lot like kinetic friction, because when an object moves on a surface or slides, kinetic friction opposes that. In this case, it's an object moving in a fluid. Now, fluid dynamics and fluids is something we're going to get to do some more with in our last unit, because we just added, last year AP added on fluids. But a fluid is defined not quite as we might think. We might want to say, oh, like water or, any kind of liquid. I think we tend to equate fluid and liquid, but fluid is actually more than just a liquid. So air is an example of fluid. Water is an example of fluid. Turns out what we would think of as like gases and liquids both fit into fluids. So even like helium gas, if you fill up a balloon, that behaves in a way that the fluid dynamics that we'll look at in Unit 6 apply to that. So it's not just, drag is not just air resistance, or not just fluid or water, or sorry, not liquid resistance. So it's more than just water, it's air included, because they both behave very similar. If something is flying through the air and experiences drag force, or if a swimmer is swimming in their lane in the water and they're experiencing drag force, that same sort of fluid dynamics and resistive force is applied to them. There's obviously some slight differences between like the amount of drag in the air versus water and so on, and how it behaves. I'm sure there's some detailed differences you could get into. But for our purposes, we're not going to get into the weeds with drag force, and we're just going to say any object in air, water, or another fluid, liquid or gas, experiences drag force. Now, this, as far as push or pull, it could be thought of as a push or a pull. So we could conceptualize or think about it as a push or a pull based on this sort of interaction there. So a visual would be a plane. You could picture the air pushing against the nose of the plane, right? The air molecules that are right in front of it are bumping into and pushing against the nose of the plane, providing some drag force. But we could also visualize as that air flows or moves along the side of the plane, sort of like the friction idea of the surfaces being rough and catching on each other and pulling on each other. You could picture some of the air molecules like pulling on the side of the plane as they sort of catch on it or bump up against it and slide against it. So almost more like friction. But yeah, we're not going to get super detailed on that. You could reasonably call drag force a push or a pull. I think there's no super correct way to do that. All right, our variable for drag force, and I guess I'll do some decent amount of color coding here so we can kind of keep things straight. We have our variable, which unsurprisingly is F with a subscript D. The units are still newtons, nothing different there. And probably not super surprising that we don't have an equation for it. There are equations that exist that that we could use for drag force, but we won't mess with this. There are equations out there we could try to apply, but we're not going to go down that road in AP Physics 1. Even in AP Physics C, actually, if you take Physics C, they do a little bit with that. AP Physics kind of dabbles in air resistance equations and drag equations. They're not the worst thing you could possibly deal with, but it requires some calculus and stuff to get through that. So we're just going to say if drag is relevant, if it shows up, it'll be something like here's 8 newtons of drag force, probably in the negative direction. If your object moves in the positive direction, you'd get negative direction for drag. So like -8 newtons of drag force, and then we'll just factor that into working with all the other forces. We're not going to have to like calculate the amount of drag force based on how fast the object is moving or what the fluid is that it's passing through. All right, last one is spring force. So our last of the 7 main types is spring force. And spring force is defined as the force in a stretched or compressed spring. Now, it doesn't have to be a spring. Um, it could be a stretched and compressed spring or some other elastic material. I think of like a rubber band. Now, the one thing there is you can't compress a rubber band. If you push on the sides or ends of a rubber band, it's just going to sort of collapse in on itself, or a bungee cord or something. You can't push them inwards and compress them like you could a spring. Now, even some springs are able to be both stretched and compressed. The springs we have in our classroom are only able to be stretched because they're coils. The coils of the spring are already right up against each other, so you can't really push them or compress them further. But there are springs that exist where you could compress them or you could stretch them. When it comes to something like a rubber band, you can really only stretch it, but that's fine. We're mostly going to have springs specifically in our problems. Um, so this force, as we're going to see in the equation in just a little bit, it depends on the K value. We're going to talk about what that is once we get to our equation more. We'll define it here and talk about it a bit. So the K value or the spring coefficient, those are kind of the two ways. Mostly it's called K value. You'll see me call it the K value, but it's also called like the spring coefficient. And it plays a somewhat similar role to the coefficient of friction. We'll talk about the equation once we get there. So this K value, this value, represents the strength of the spring. So it represents the strength where larger values mean a stronger spring. So if your K value is super, super big, you've got an insanely strong spring. If your K value is really small, you've got a very weak spring. So I'd picture like the shock absorber springs on a massive semi truck or train or something like that. There's these huge springs. Those are going to have a really big K value. Um, in like a pen or pencil, the little, if you've ever taken them apart, because I used to like to take apart pens and pencils and pull out the spring and hopefully not lose it. But those little springs in your pen or pencil, those are more flimsy. So those would be a really small K value. They're weaker. Yeah. Okay. Um, so the amount of force in this spring depends on the K value or spring coefficient and on how far the spring is displaced from its natural length. So the natural length of a spring is if it's relaxed, if the spring is just sitting there, that's its natural length. If you then begin to stretch or compress it, you're changing the length of the spring from its natural length. And let's say it started as a 3 centimeter spring. You stretch it out so it's 5 centimeters in length now. The displacement, how far it was displaced, would be 5 minus 3. So you displaced it by 2 centimeters, stretching it out from its natural length of 3 to a length of 5. So we're always finding the difference between, well, how long was the spring when it was just sitting there, and how long is it now that we have stretched or compressed it? So that difference between the lengths of the spring, the natural length, and the stretched or compressed length is how we get how far it was displaced. All right, spring force can be a push or a pull. And that's just because if you push on a spring, you compress it inwards, you push inwards, it's going to push back outwards, right? That would be the push. If you grab a spring and you stretch it, you pull from the two sides, it's going to pull back inwards. So depending on whether you compress it, you'll get a push, or you stretch it and you'll get a pull. It could be either one. Okay. Variable is pretty straightforward here. It is what we'd expect, Fs, along with the same old units we've had this whole time. Spring force in newtons. All of our forces showing up in newtons. And the equation for this looks like this. So our equation says that the amount of spring force, Fs, is equal to the negative K delta X. Now, there's a couple things that are important to point out here. First is K itself. There's that K value we talked about. The K value or spring coefficient. That's what this is. So this is the K value. And the K value itself is positive. So all K values we run into for any spring, no matter what, even if you get a really weak one with a K value of 8, or a really strong spring with a K value of 3, 4, 500, something like that, they will all be positive. The negative sign is just in the equation, right? It's negative K times delta X. The negative sign does not indicate that your K values are negative, right? They themselves are actually positive. Okay. And the units are newtons per meter. Okay, awesome. So from here, we're going to look at this displacement real quick. This displacement is just, well, actually, we can draw the arrow right here, right? This is the delta x is how far the spring is displaced. So we could think of this as, again, your stretched or compressed length minus the natural length, or the difference between those. We'll see some examples in class, and we'll be able to talk more about this. But if you have a spring and you squish it in, you compress it to the right, then you might get a positive displacement if you assume that right is positive, and it just depends how far you compress it, right? If the natural length was 0.4 meters and you compress it so it now has a length of 0.2 meters, then you compressed it by 0.2 meters. So that displacement is always going to be how far did you stretch or compress the spring from its natural length to the length that it is now. And that's your delta x. Now, one last thing that's important to mention with this, uh, k itself is always positive, so negative times k or negative k will always be negative. So this first part will end up being negative, not because k is negative, but we're multiplying k times -1, essentially. So that means that if your displacement is positive, then your spring force will be negative, and vice versa. If your displacement is negative, you'll get a negative times a negative, and your spring force will be positive. So spring force and displacement, these two vectors, spring force is a vector, has direction, displacement is a vector, has direction, they are always opposite in direction to each other. Meaning, if you compress your spring to the right, positive delta x, the spring force will push back to the left, negative spring force with a positive delta x. If you stretch out your spring to the left with a negative delta x, for example, then you'll get a positive spring force pulling back to the right, which makes a ton of sense with springs because whichever direction you compress them or stretch them, they're going to push or pull back the other way. So we always expect that if your delta x is positive, spring force should be negative. If delta x is negative, spring force should be positive. So we can see that just from the equation. That's this negative sign here, making sure that delta x and spring force always have opposite signs to each other. One is positive, one is negative, because of how springs work. And that the equation then matches with that. Okay, and that's all of our types of forces. So we can move on to talking a wee bit about mass. Mass is something we hopefully understand on a pretty basic level. We're about to get into some Newton's laws in a while, hopefully later in this video, but we'll see. Newton's laws deal with mass, one in particular, Newton's second law. But yeah, let's remind ourselves a definition of mass. So we'll go ahead and write that here. So mass, it also shows up in gravity, the force of gravity equation that we already saw, mass times 9.8, or mass times the acceleration of gravity on any planet, not just Earth. We'll find you the force of gravity from our force of gravity equation. So mass is the amount of matter or material that makes up an object. So if we were to count mass on a fairly basic level, we might look at something like atoms, right? How many atoms make up an object? Now, we don't measure with that because the amount of atoms in an object is a lot, a little bit too big of a number for us to use. But that's the idea of it, right? Is like, if you really get down to it, how much of this object is like actual empty space, like nothingness, and how much of it is like atoms, molecules, physical, actual matter that makes up the object. Okay. And that's why you think of like, you know, the density of something like lead, if you had lead, or even like the material that makes a bowling ball. Bowling balls are pretty dense and they're heavy, and like we know they have a lot of mass. And so that's a good example of, right, a lot of matter is packed in there. A feather, and we'll hopefully watch a video comparing bowling balls and feathers. I mentioned them with force of gravity and how fast they fall and how much they accelerate and all that. But the reason the Earth pulls so much more on a bowling ball than a feather is the mass, because a feather just doesn't have that much matter in it, right? In order for birds to fly and be lightweight, the amount of atoms and molecules that make up each of their feathers are not that many. So compared to the large amount of matter or mass that is in a bowling ball. Okay, so note that this does not change. So it does not change if you go to another planet. So you go to another planet, you are the first astronaut on Mars or something like that. And you still have the same amount of matter or mass. Now, of course, you could have lost or gained weight through like eating and things like that. Like if you ate a lot or not, depending on how much you like worked out and ate and what you ate on your flight to Mars, you could, based on that, you could have more or less mass. But let's assume you like keep up your same routines or keep up the routines necessary to not really lose or gain weight in that way. And you just like show up the same when you get to this other planet. So the amount of matter or material that makes you up or makes up an object doesn't change if you suddenly transport it. Maybe a better example is the bowling ball. If you put a bowling ball in the spaceship and you take it out on Mars, it still has the same amount of atoms and molecules that it had on Earth, unless you took a chunk out of it with a chisel or something. So um, this mass doesn't change, but the force of gravity does. Which means if you were to step onto a scale that measured force, and most of our scales that we use do actually measure or depend on force, they're like force sensors. So if you went to the moon and stood on a scale, or you went to Mars and stood on a scale, you would register something different there because the force with which Mars pulls you or the moon pulls you is different from Earth. Same thing if you went to like, I don't know, the International Space Station or just like even the top of Mount Everest has some different forces by a little bit than the surface of the Earth. Okay, so that's mass. We just want to remind ourselves of the variable in the units. There's not an equation for it. We just like measure or know the mass. Um, we'll involve equations, mass in equations for like Newton's second law and whatnot. Lowercase m, it's a scalar value, right? So there's no direction on it. The units are kilograms. You would have used base units of grams in chemistry because the things you're dealing with are like um, whatever like compound you're dealing with or chemical you're dealing with or a thing that you're mixing together or using in a chemistry lab. It's small enough that grams were the appropriate units of measurement when you did chem. Physics, we're dealing with like a car or a person or a bicycle or something that's more suitable to be measured in kilograms. So even though we'll have small things like our small objects could be 0.002 kilograms or something, we have enough large objects that are 1, 2, 3 kilograms, something like that, that we just use that as our default or base units. So we're going to stick with kilograms as our go-to. So if you have something in grams, go ahead and convert it into kilograms for our problems and our equations that we're using. And of course, we don't put a direction on it. It's a scalar, so we don't say 12 kilograms downwards. Now, the force of gravity, which is different from mass, the force of gravity would be downwards, and we could calculate it by taking that 12 kilograms times 9.8 on Earth meters per second squared, the acceleration of gravity. Okay, so that's mass. Just a quick reminder on it and seeing how we use that. One last thing we'll do before we move on to free body diagrams is we can also show with mass and with the equation. So based on the force of gravity equation and what we know about mass now with the units, we can show exactly what the newtons. We can show that newtons as a unit are equivalent to kilograms times meters per second squared. So let's talk about that and how we know. Well, let's start with our basic force of gravity equation. Force of gravity is equal to the mass of an object times the acceleration of gravity. And if you were on a different planet, you could use something that isn't 9.8 or 10, but on Earth, we would just use 9.8 or 10 if you're doing AP, because AP likes to round to 10, and you'd multiply it times the mass. So a 12 kilogram object would experience 120 newtons of force from 12 times 10. And it would be directed downwards. Because unlike the spring force equation up here, there's no negative sign in front of the scalar. So force and acceleration of gravity are always in the same direction as each other. So if g is negative, so is the force of gravity. If you decide that down is positive, so g is positive, so is the force of gravity. So these two vectors, force of gravity and acceleration of gravity, will always have the same direction as each other in this equation. Versus the negative sign in the spring force made sure that spring force and delta x have opposite directions. Anyways, that's a little bit off track. So I'm going to write this equation, but just with units. So an amount of newtons, now this could be 10 newtons, 20 newtons, we don't really know. There's some amount of force in newtons, which is equal to some amount of mass in kilograms times some amount of acceleration, and our units for acceleration are meters per second squared. So this, oops, not meters squared. This sort of dimensional analysis piece of breaking down an equation into just its units, or replacing the variables of force, mass, and acceleration with the units of force, mass, and acceleration, can show us, well, what is a Newton? 1 Newton is the amount of force it would require to accelerate 1 kilogram of mass at 1 meter per second squared of acceleration, is one way we could think about that. So a Newton is the same as a kilogram times meter per second squared. That can be a useful reminder of when you're working with units and you're like, okay, how do I get to a Newton, or how do I know how many newtons this is? Newtons are the same thing as kilograms times meters per second squared, or mass times acceleration. Okay, well, let's talk free body diagrams. So these are ways to draw forces. We've got all kinds of info now about types of forces and variables and units and equations and all that, but how do we draw them or visualize them? So let's get into it. So these are free body diagrams. AP will also call them force body diagrams. So I guess we could do free body diagrams, or we'll do this. We'll do free body or force body diagrams. I like calling them free body diagrams. I've done that for as long as I have done physics, basically. But you can join AP and call them force body diagrams if you want. Okay, let's talk about what they are. So obviously, we'll start with just the way to draw forces as vectors. So the best way to draw forces is just the best way to draw vectors, back from our beginning of Unit 1. No different from our velocity, acceleration, displacement. We're using arrows. So the best way to draw forces is as an arrow. All right. As we determined, this is the case for most vectors, right? Okay. So free body diagrams or force body diagrams, we're going to abbreviate them FBDs. All right, free body diagrams. So FBD. If you're drawing an FBD, these are excellent tools to show all the forces. And this is an important part here, all the forces acting on an object or system. We'll talk about systems in a little bit. So object or a system. We'll talk about this later. We will get to systems, but we're going to hold off on that for now. So you have it. Let's just look at objects for the time being. So you have an object like a box sitting on the floor or a person standing in an elevator or whatever it is. Um, and you want to look at a free body diagram to show you the forces. Specifically, free body diagrams are going to show us the forces acting on that object. So if the box itself on the ground is pushing or pulling against something, like the box is pushing on the ground, we would not draw that on a free body diagram for the box. Um, so that is a key thing, is we want to make sure we draw or show the forces that are experienced by the object that we're looking at. Okay. Um, so we're going to do this in order to use force equations to analyze and solve problems, as we tend to do in AP Physics. Okay, cool. So we're going to say below are the rules for drawing free body diagrams. There are some rules. Okay, so the rules for drawing FBDs are as follows. First off, you want to start with a simple box or dot. I prefer boxes. AP prefers their dots. I just think on a box, you can not only label what it is, which is our next rule or way to tell what object you're talking about. I think it's easier to label a box like inside it. And then it's also easier to draw a bunch of forces acting on a box because you got more room to draw instead of just a little dot. But AP tends to stick with dots. So start with a simple box or dot representing either the object or system. And AP uses dots. So AP really likes their dots. I preferred the boxes, but either one is fine. All right, so we're going to then um, label the box or dot. To clarify, what these forces are acting on. So we're going back to that. We want to draw the forces acting on an object or system. So another way to say that is what forces are experienced by the object or system that we are looking at. So if it's a box, again, we want to see what pushes and pulls are acting on the box, are experienced by the box, not what pushes and pulls is the box putting onto something else. So that's an important piece. All right, then we want to draw the forces as arrows. And we're going to starting at the box or the dot. And pointing in the direction they are acting. So if you have a force acting to the right, you'll start that arrow on the right side of the box or dot and draw that arrow pointing to the right in the direction it is acting. Then the relative length, so how long or short a given arrow is, the relative length of the arrows should match how large or small the force uh, generally is. Now, this isn't a perfect science. You don't have to get out your ruler and say, well, this force is 7 newtons and this one is 10 newtons, so I better make sure it's exactly 7/10ths of the other length of the arrow. Don't worry about that. But if you have forces that are 7 newtons, 10 newtons, and 14 newtons, the 7 newton force should be drawn with the smallest arrow, then the slightly longer one for the 10 newton, and then the longest arrow for the 14. Just show them in order and generally try to keep it as proportional as you can, but don't worry too much about that. All right, last one. Actually, sorry, I realized I should edit this. I'm going to rephrase this just a little bit. My apologies. I feel bad if you took notes in pen. I do want to emphasize this is magnitude, right? Because I think that is a really important piece of vectors is, okay, what is the magnitude of this vector? That's, of course, the number itself, how big it is. 7 is a smaller magnitude than 10, which is a smaller magnitude than 14. So force magnitudes are really what we're talking about when we say how small or how large, how long should the arrow be. So your magnitude, even if it's positive or negative, right? You could have a positive 7 or a negative 7. Those have the same magnitude of force. So that's important. All right, now AP generally does not want you to draw components of forces. Now, this should ring a bell. Components for vectors should bring us back to some sines and cosines, some right triangles. This was when we drew like an angled vector and said, hey, we can look at the x and y components, the parts. So we did sine and cosine, sine theta, cosine theta. We did this with projectile motion, where we said initial velocity can be broken into two parts. There's a horizontal initial velocity and a vertical initial velocity for projectiles. So these components, we're going to be doing that with forces. We're jumping ahead a little bit there to angled forces and using sine and cosine with those, but it really operates pretty much the same way as our other components of initial velocity when we did projectile motion. So AP generally does not want you to draw components of forces. So if your force is angled, you have an angled force at some angle, um, simply draw the entire or total force as an arrow at an angle, or at that angle specifically, whatever it is. If it's a 30-degree angle on your free body diagram, do not split that angled force of 30 degrees into how much of it is x, how much of it is y. Draw those x and y components on the free body diagram. Now, as much as I say that, it's very useful, I think. So I disagree with AP on this of like I think there's a high amount of usefulness in drawing force components on a free body diagram. When we'll look at that later when we get to angled forces and Newton's laws, but I think it's actually very handy. I think it's good. Um, yeah, but we can AP and I can agree to disagree, and with their rules, with their grading or rubrics, you don't want to draw components. You just want to say, hey, if this force is angled, cool, I will draw it on the free body diagram at an angle. All right, let's get some examples of this. We got a lot of rules. Let's see some examples. We'll just present some scenarios and situations in which something could happen, and we could draw a free body diagram for it. So let's just do a falling object. We'll put that right below here. All right, I'm going to start with a box. Now, you could do, if you know it's a watermelon, you could label it as that. If you know it's a backpack, you could label it as a backpack, whatever it is that's falling, right? For now, I'm just going to put M in there. Now, M indicates that it has some mass. That's just kind of a frequent thing we'll do in physics is like, here's an object, it has some mass. You might call it M1 or M2, which is not very creative on the parts of physicists for naming or labeling objects, but sometimes we just call them M1 and M2. I think of like Thing 1, Thing 2 from Dr. Seuss, if any of y'all have seen or read those. But yeah, sometimes we'll just call it M for the object, whatever it is. Okay, but the important thing here is we draw a box or a dot, but I'm going to do a box, and we draw the forces acting on it. So actually, I'm going to scoot it up a little bit here, just a wee bit, because I want to leave plenty of room for things. All right, I'm going to draw two forces. One is gravity. We know gravity acts downwards. So again, I'm going to start on the box itself, draw an arrow straight downwards, and then I guess I didn't explicitly say um, label the forces, but you don't have to all the time. It's just really helpful if you're wondering like which force is this? This one's gravity, force FG. So labeling, we did say to label the box, but labeling the forces too. We could maybe sneak that in there. I don't want to move everything, but label the forces if possible. You're not always going to have to do this. It's just really nice to be able to look at your situation and say, okay, I know what each force is. I know that this one in particular is gravity. I know that this one is normal force, whatever. Okay, so our object's falling through the air. Now, if we were to do the most simple possible free body diagram, this would be it. We'd be done. I'm going to throw one more force in there because it's one that we tend to ignore, but if it's falling straight downwards, we'd have a little bit of drag force. We'll throw that in there. We don't have to do the math with it right now, so we can afford to pop a drag force in without worrying about the math required to calculate that drag force. And as we'll see later on, even if we said gravity was 20 newtons and this was 6 newtons, we could still do some math with that when we get to Newton's laws to solve for things, even though drag force can be tricky with some of its equations. So there's a falling object. Cool. We'll do another one. We'll do a box that is pushed along the floor. Oh, I know I'm getting to the end of my amount of allowed characters when I start getting really wacky writing. It like slows down when I get to the end here. All right, let's do a box. Now this is a box that is actually a box, so we'll label it as such. I guess I should draw it a little bigger if I'm going to write inside of it. This is a box. There you go. It's a box that is actually a box. So we're going to push on it. Now, let's say we push to the right. So you or I come along and we push this box directly to the right. We could push at an angle, and once we have angled forces, we'll include those, and we'll talk about how they affect gravity and normal force. There will be some aspects to that with angled forces. But for now, let's just say you push it to the right. Now, even though you might be tempted to draw that push like this, like you come along, you come from the left side and you push it to the right, that's not how we want to draw our arrows. Remember, we want to start the arrows with their tail at the object. So we'll draw it like so. And there's our applied force. So the person pushes on the box. Cool. Let's draw gravity, of course, because gravity is still acting. Just because the box isn't like falling, we still have a force of gravity. And because the box is on the floor or on the ground, there's also a normal force. Normal force is the supportive force pushing directly against gravity from the ground to support the object and prevent it from accelerating down into the ground. And in this case, it exactly matches gravity. There is a trick you can do here, which is not necessary, but if you want to draw like a little line through these, a horizontal line in this case, or you could do vertical lines if you're dealing with horizontal forces, you could do lines like that. But this just shows that gravity and normal force are equal to each other. It's just kind of a neat little trick you can do to say like maybe I didn't draw the arrows perfectly the same length as each other, but this is a reminder or indication to whoever's looking at the free body diagram, hey, these are equal. Gravity and normal force are equal to each other in this scenario. And we're going to throw a little bit of friction in there. So friction acts against, we'll just say that our object is already moving. So this would be kinetic friction, FFK, force of kinetic friction, and it's acting opposite to the direction that the box slides and moves as we push it with an applied force to the right. Friction acts to the left. Okay, so there's a free body diagram for that, right? Keep in mind, we're drawing all the forces that are acting on the box. The earth pulls downwards on the box. The floor below pushes upwards on the box. We push on the box as a person, sliding it along the floor. The friction, uh, normal force and friction are both forces from the floor, but one of them pushes up from the floor to support it against gravity. One of them pushes or pulls to the right, or sorry, the left, to oppose and slow it down a little, or try to slow it down as we slide it. If we have enough applied force, we can succeed in actually speeding it up or pushing it across the floor, so it's not going to slow down and stop. But friction is trying to slow down and stop the box. If we take our hands off of it, it will immediately begin to slow down and eventually stop due to friction. Okay, let's see. I don't know. We could maybe do one more. Let's think something with springs. I wonder about tension. There's a good number of ways you could like make weird situations involving tension and spring force and something else. And so there's lots of options. In fact, a very common one here might be if we pull the box with a string or rope. So we attach a rope to the box and pull it across the floor horizontally. This would actually become a force of tension acting on the box, even though you could probably make the argument that you could still call it an applied force, because even though we, the person pushing or pulling the box, um, are really the ones applying or using that force, if there's a rope attached to it, the tension in the rope is transferring that applied force. So if we pull with 20 newtons of force and that transfers through the rope, the box experiences a force of tension as the rope itself pulls on the box. So it's just kind of, that's neither here nor there. Like you could probably put applied force or tension in that scenario, but it's an example where you could put tension in there. Let's see, springs. Sure, we'll just do like an object launching off of a spring. This would be like your projectile launchers back in Unit 1 when we did projectile motion and you tried to hit targets. Right as your object launched off of the spring in your launcher, we can draw a diagram. Now we're just going to do like a horizontal launch for this. So your object, which we'll just go back to M. In reality, it would be like one of those little plastic balls. So you could, if you drew a bigger box or left more room, you could label it as a ball or whatever you're launching. So our object that has some mass, which probably would be like one of those plastic projectiles that you launched. The gravity's acting on it at all times. As long as it's near the surface of the Earth, you get some amount of gravity. So we'd want to make sure that's almost always going to go on every free body diagram, unless your object is in outer space or somewhere where there's no gravity. The force of gravity will be acting on it. Now, as it rests in the like tube or chamber that it's going to be launched out of, we could say there's some normal force. This is like a horizontal launch situation. So we'll say there's some normal force preventing it from going downwards. We could once again indicate that those are equal to each other. So gravity tries to pull it down or pulls it against the side of the tube or launcher, but normal force pushes back up and prevents it from going anywhere in that regard. But then we've got a big spring force. So your spring force is launching it out of the tube. Now you could include friction or drag. There's any number of things here. Like you could say there's probably friction in the tube itself as we launch the object out. So we could draw that in the opposite direction. But the main thing here is just to show that when a spring acts or pushes on something, so it's launching your object to the right, blasting it out of your projectile launcher to the right, that spring force would be drawn just as an arrow to the right. It's probably really large because we need some significant amount of spring force to launch it and get some nice velocity so it flies through the air. Okay, cool. I mean, we'll see lots of other free body diagrams. I wanted to incorporate a bunch of different forces like drag and friction and gravity, normal applied, spring, tension can go in there too. But yeah, cool. We'll see plenty of those and we'll get some more chances to draw free body diagrams. Let's wrap up with at least introducing Newton's laws of motion. I hope I have enough little characters left here. We'll find out. All right, so Newton's laws. These you should be somewhat familiar with from eighth grade science or whenever in the past you've looked at this. We are really getting to the point that the writing utensil or the characters are really struggling. All right, first, well, we'll establish that there's three of them. So that's important. We'll get into some further detail and analysis probably in another video, but we're gonna write them out here. 1, 2, 3. We're gonna go into like a little bit more detail here than you would have in like eighth grade or whenever you saw these. So the first law, and I might have even asked you in class as like a review activity of like who can remember what they know about the laws of motion, and someone probably said at some point, objects in motion stay in motion until acted on by a force or something like that. So that's the idea of Newton's first law. But we're going to be fairly specific in some of those terms we talk about an object and what it's doing. So we're going to say that objects objects that are either at rest. Uh-oh, they're already warning me that I'm approaching my limit of elements. Well, we're gonna get as far as we can. We'll see what we can do. Or in constant velocity motion, remain that way which means if they're at rest, they remain at rest. If they're in constant velocity motion, they remain in constant velocity motion until uh-oh. Well, you know what? I might what I might do is I'll throw this all together in a we're gonna try this. I'm gonna make a new page, which I haven't done, but it doesn't seem like it'd be too hard. Look at that. And sadly, I'm gonna have to rewrite some of this, but that's okay. We'll figure it out. So nice thing is now that I'm rewriting on a new page to get my elements in, it's all fast and well, a little better quality here, I think. Or maybe it's just oh my goodness. Now I just don't know what's going on. Hmm. Okay. Anyways, Newton's laws of motion. We're gonna have to do a little rewriting here, but that's fine. One, two, three. So the first law states that objects that are either at rest or in constant velocity motion remain that way. So if they are at rest, they remain at rest. If they are in constant velocity motion, they remain in constant velocity motion until acted upon by an unbalanced outside force. Okay, so let's break this down. We've added a couple things beyond the basic definition of objects at rest remain at rest, objects in motion remain in motion until acted on by an outside force. Something along those lines you would have encountered back in a previous science class. But so if an object's at rest and it's not moving at all, or if it's moving but it's moving with a constant velocity, it will remain that way until acted on by an unbalanced outside force. So what this means is something sitting on the table, let's say your computer or your water bottle sits on the table. Right now it's got gravity and normal force acting on it. You can look around you and see anything that's sitting or placed on the table or floor near you. Gravity pulls down, normal force pushes up, and they remain at rest. So those forces are balanced. There are forces acting. There are outside forces acting on everything you see around you. But in the case of everything at rest on the floors and tables, those forces are balanced. So the objects will simply remain at rest. If you want to pick up your water bottle, you come along and you provide an applied force upwards that is greater than the force of gravity pulling it down, and then you lift up your water bottle to take a drink. So that object only remained at rest until you came along and unbalanced the forces. You provided more upwards force from applied force than the downwards force of gravity, and that unbalanced outside force caused the object to accelerate and begin to move upwards as you got a drink. Constant velocity is a little harder to visualize. Cruise control is a way we achieve that on Earth. So if your car is in cruise control, that means that the amount of force, we'd call it like an applied force or like an engine force or driving force. So whatever the force from your engine and your wheels and your axle and all the parts of a car, you've got a forward force propelling you or pushing you, trying to get your car to go forwards. You've got some drag and friction resisting from like the air outside your car and whatnot. So cruise control means you have exactly balanced the forces going backwards, like drag and friction, with a force going forwards from your engine. And if that happens, you maintain constant velocity motion because you've balanced all the forces. Once you're done with cruise control and you hit the gas because you want to actually speed up, or you hit the brakes because you want to slow down, what you're doing then is you're unbalancing the forces. If you hit the gas, you're providing more forward force than the backward forces of drag and friction. And then if you hit the brakes, you're kind of turning off the forward force, right? You're saying I don't want the engine to provide any force going forwards anymore. Instead, you're going to actually add in some more friction and drag from the brakes going backwards to slow down your car so you can stop. So when you want that constant velocity motion to end, you provide an unbalanced outside force by hitting the gas or brakes to yeah, to provide a total force that is forwards or a total force that is backwards to speed up or slow down your vehicle. Another great example is satellites or space probes like Voyager. We sent Voyager out into space. There are actually no forces whatsoever. Well, assuming it's out in deep, deep space, which it almost assuredly is. There's a lot of space out there. If it's far enough away from planets and moons and suns and all that, then there's no forces whatsoever. So yeah. Anyways, I don't want to ramble too much about these, but it's saying that if something is at rest or if something is moving but with constant velocity, it will just keep doing that. So Voyager keeps going through space forever and ever and ever. It just keeps going and going and going and going. And the only way that changes, the only way it speeds up, slows down, or changes direction with acceleration is when it's acted on by an unbalanced outside force. Cool. That's the first law. Second law is a lot easier to write because it's just an equation. And it says, you've probably seen it before. We'll do a sum. This is our Greek letter sigma, indicating a sum. Sum of forces equal to mass times acceleration. Now we'll get into some more details on this. We'll talk about like X and Y direction of forces and all that sort of thing. We'll get into components of forces and whatnot. But for now, we're going to say the sum of forces acting on an object. So this is either your sum of forces or your net force. So net, I usually think about this in terms of finances. Your net paycheck, if you get a paycheck, your net is the amount you just get paid. Like let's say you get $1,000 in a paycheck for something. If you got $1,000, some of that would get taken out, right, to taxes and whatnot. So the net is like once all of that has been removed, once you've accounted for all the other things going on, now you get your $1,000. If not for taxes and other things, you might have gotten $1,500 or $1,300 or whatever. I don't, depending on what your taxes are. But that's like your gross. They call it gross income and net income. Hopefully, if you take personal finance or have taken it, you would talk about that, right? So gross income is like if you weren't getting taxed or Social Security or whatever taken out of your income, here's the amount you would get. But net income is after we've accounted for everything, how much are you actually getting? And that's the idea of the sum of forces. Because if you have like a positive 50 Newton applied force and a negative 12 Newton force of friction and a negative 6 Newton force of drag, you're going to add up or sum up all of those forces when we do these equations with Newton's second law. And you're going to say like, all right, sure, we have 50 Newtons in the positive direction, then we have 12 Newtons in the negative direction, then 6 more Newtons in the negative direction. But after we account for all of that, what is the net force acting, or what is the total force result from all those forces? Like at the end of the day, how much force is ultimately pushing or pulling left or right on this object, or up, down if you're talking vertical. So that's your sum of forces. You're just adding up. You're saying, well, we got positive 50, and then we got negative 18, and then we got negative 3, or whatever your values are. And you're summing those up to determine what is the net force. So once we add up all the forces acting on an object, that is equal to the mass of that object times the resulting acceleration for that object. So you could write this out in words. I don't generally do that, but you could say the sum of forces acting on an object is equal to the mass of that object times its acceleration. One quick thing to note with this equation, we also pointed it out in some of our other force equations. These vectors, force and acceleration, are always going to be in the same direction as each other. Because mass is a scalar. Mass is always positive. You don't get negative 5 kilograms. It's just 5 kilograms. There is no negative mass. It's like time. There's no negative time. There's no negative mass. So these scalars, that we deal with. We're just going to have a positive mass. Meaning, if your force is positive, your acceleration will also end up being positive. If your force is negative, so is your acceleration. So the force and acceleration vectors from this equation are both positive or both negative. If you have a positive net force, so you could think of that as a competition. There's the positive forces pulling or pushing one way, the negative forces pushing or pulling the other way. We're going to add up and see who wins. If the positive forces win and there's a net force or total force in the positive direction, then your object accelerates with a positive acceleration. If the negative forces win and there's more forces negative than positive, you get a negative net force and your object gets a negative acceleration. So yeah, that's the basic summary of the second law. Is it's looking at all the forces acting to say, hey, let's look at a free body diagram or something, and from that free body diagram, we'll determine, okay, I've got 5 different forces or 4 different forces acting on an object. We're going to sum up the forces, find what the total or net force is, then that is equal to the mass of our object that's experiencing those forces times the acceleration. How much does it accelerate? And this is really the key to our whole essential question for the unit. The essential question was, what causes changes in objects' motion? And the answer is forces. Now with this, we can say the result of all the forces acting on an object, when we sum up all the forces acting and find the net result of that, that is equal to the mass of an object times its acceleration. So it directly shows how force affects acceleration. If you get a really big force, like you push something really, really hard, you will get a large acceleration. If you provide a very small amount of force, you get a small acceleration. But it also depends on the mass. That's the cool part of this. If you've got a 10,000 kilogram object, sure, you could use 100 newtons of force, but your acceleration still won't be very big. If you have a really light object, like 1 kilogram, then 100 newtons of force will provide a very significant acceleration, because 100 equals 1 times acceleration. If you use 100 newtons of force on a 1 kilogram object, your acceleration would be 100 meters per second squared, which is quite a lot. Yeah, so there's lots of cool ways to connect the way things actually work to Newton's second law of motion with different masses, experiencing different amounts of acceleration depending on how much force acts on those masses, how much net force. Last one, let's wrap this one up. So Newton's third law, the short version is for every action, there's an equal and opposite reaction. This one, we're going to write a much longer bit to it. So here we go. When an object exerts a force, by object, we could also mean person. When a person or object exerts a force on a second object, the second object will, and this is always true, will exert a force back on the first object that is equal in magnitude but opposite in direction. Okay. So what do we mean by this? We mean that, let's say I push on the wall. I go up to the wall and I push on it with 5 newtons of force. The wall pushes right back on me with 5 newtons of force also, but in the opposite direction. Think of like baseball. When there's a contact between the baseball and the bat, The baseball exerts a force on the bat exerts a force on the baseball, and those two forces are equal in magnitude but opposite in direction. Um, this is why you get some like rebound sometimes. If you hit something really hard with a bat or a tennis racket or something like that, it's possible you could get some amount of rebound, like your racket or bat almost wants to go back in the opposite direction from which you were swinging it because there's a large force from the ball. Like you swung the bat and you made the bat put a big force on the ball, but now the ball puts the force back on the bat. So same thing as like if you kick something really hard, maybe your intention is, I stubbed my toe on the sofa, so I'm gonna show the sofa what's up and I'm gonna kick it really hard. Well, you might want to put a lot of force on the sofa, but as soon as you provide that force and your foot comes in contact with it as you kick really hard, well, the sofa is the second object. It's going to put a force back on your foot that is equal in magnitude. So the harder you kick the sofa, the harder the sofa is going to put a force on you, and it's going to hurt. Right? So that's why, like, not that I encourage anyone to get in a fight, but one of the things that I've heard about like people who like boxers or people who would fight with their fists, especially if they were using like bare fists, if they punch someone really hard, they might, damage the other person, but they might also hurt themselves because you can break all the fingers in your hand by punching someone. The reason being you put a force on them, but as exactly as hard as you punch, the force goes back into you. It goes into your hand, and you could break a finger or your hand or whatever. So this idea of like, and a great example is a skateboard or a chair or something that's on wheels. And I might even do this in class where like if I push on the wall really hard while I'm standing on a skateboard or sitting on a chair with wheels, what happens is the wall doesn't move because it's very sturdy and stable and attached to the building. So my wimpy 20 Newton force doesn't do anything to the wall. But actually, the force from the wall back on me can cause me to accelerate. With Newton's second law, we could say if I experience a force from the wall and the net force acting on me is, 20 newtons from the wall pushing on me, it can result in then an acceleration for me. So even though I'm the one pushing on the wall, like I'm trying to get the wall to move, I'm the one who ends up moving because I'm on wheels or I'm able to move. And if I push really hard, the wall pushes back and I start to roll across the floor in my chair. So there's lots of evidence of this in many scenarios where like you have two objects pushing or pulling and you can see how, oh yeah, there's two forces. Object one pushes on object two or pulls on it, and then object two pushes or pulls back on object one. The Earth and the Moon are great examples of this. Earth pulls on the Moon, causing it to stay in orbit. The Moon pulls right back on the Earth with the same amount of force. The results being the tides, right? Tidal effects are the Moon pulling back on the Earth because the Earth is pulling on the Moon. Yeah, so Newton's third law is just anytime, anywhere that an object exerts a force on a second object, that second object exerts a force back on the first that is equal in magnitude but opposite in direction. Whew. Okay, we'll do some more details on this. I want to talk about like inertia and the law of inertia, which is the first law. I will talk about the use of the second equation where we can do math with it and talk about x and y directions. We'll talk about equilibrium. We'll talk about the third law and third law types of problems. We'll do some specification. Gravity and normal force are often confused for an example of the third law when they are not. We'll talk about why gravity and normal force are not one object pushing on a second, the second pushing or pulling back on the first or whatever. So yeah, there's plenty to break down with these, but we're gonna wait for our further analysis of Newton's laws for the next video. So we've got them written down. We've got the basics here for Newton's laws of motion, and we'll have to expand on those later. Okay, well, that's gonna do it for this one. So we'll see y'all in class, and have a good one.